National 5, great to see you. I just wanted to use this flame as an analogy today to say that this family, this YouTube channel is on fire right now. But you know what we can do? Together as a family, we can turn this average, not so warm flame to a roaring flame. And the only way we can do that is by liking and sharing this channel. Let's go from the orange flame to the blue flame. I believe in you, family. Let's do it together. Did you like that National 5? I know you did. Well, it's a very true point because we've only got 41 more subscribers to go and we are so close to the 200 mark before Christmas. You guys are making it happen. But I wanted to share a new shout out today, alright? And this shout out goes to those picking higher and continuing the cause. If you're in National 5 right now and you're picking higher, this shout out goes to you. If you're in my National 5 class and you're not thinking of it higher, I think you should really, really think again, and you know who you are, alright? So that shout out goes to those who are definitely picking higher next year. Well done, you guys. Alright? But if you are picking higher, comment below so we can see the family who are taking on the cause to the next stage. Alright? Okay, we're going to be moving on to the next part in electricity now, and we're going to be talking about Ohm's law. Okay? Now, this again will be fairly quick. I'm actually going to take a snapshot of the layout that we're going to be doing because it's an experiment. I'm just going to show you what it looks like, talk you through it by just kind of moving around, but I'll be cutting to that in about 2 or 3 minutes. Okay? So, we're going to be learning to complete an experiment to derive an equation, which is Ohm's law. We can't do the experiment on a video, but we can show you how roughly to do it. So, we're going to be doing an experiment. What is Ohm's law? We don't know Ohm's law yet. We're going to try and prove Ohm's law. So the aim of this experiment is designed to find the relationship between current and voltage for a fixed resistor. Okay? So to find the relationship between the current and voltage for a fixed resistor. That's what we're trying to do today. Okay? Now, we've been looking at circuit diagrams. This is one that we're going to be using for the experiment. We've got a supply voltage and we've got a current or ammeter in series. Okay, so it can only be used in series. Okay. We have a resistor that we're going to be measuring the current and voltage for, and we've got a voltmeter. Okay, that's what we're going to be doing. Now notice it's a variable DC supply, because what we're going to do is we're going to change the supply voltage here, and then measure the voltage and current when we change that DC supply. Okay. Now, using an ohmmeter, we're first of all going to measure the resistance of a resistor that we will use. Say a 15 ohm resistor, and we're going to note that in our workbook. Now, if we want to use a 15 ohm resistor, we need to measure it. Why do we need to measure it? Well, we need to actually see if it's a 15 ohm resistor, because sometimes in the manufacturers they say 15, but it can sometimes be 16 or 14, and we need to know exactly the right value. And to connect an ohmmeter, you don't actually need to connect it to a supply or anything like that. You just connect an ohmmeter, plug it into the resistor, and you see the resistance of that resistor. So once you did that, or once you've done that, we're going to build the circuit as shown. Okay. Now I'm going to jump into that in a second, but let's just see what we have to do. We're going to adjust the variable power supply until the voltage reading on the voltmeter is 0.5 volts. So we're going to change that until the voltmeter reads 0.5 volts. At that point, we're going to then record the corresponding ammeter reading. Okay, so we're going to change the DC supply. The voltmeter is going to go to 0.5, and then the ammeter we're going to record in our notebooks. We're going to repeat that for other voltages until we get to, I think, 3.5 volts, going up in 0.5 volt increments. And we're going to record the current each time. We're going to repeat the experiment a second time in order to get an average, so that means we can have more accurate results. Now, what I'm going to do is I'm going to show you this setup. I'm going to talk you through it by just scanning with my phone with a very well set up Ohm's law experiment for anyone at home. Okay, so I'm going to start to that now. Okay, so National 5, here we go. Here's a setup for Ohm's law experiment. You can see we've got the supply voltage, okay, set at 0 at the moment. We've got an ammeter connected in series to a light bulb, or in this case what we were seeing is a resistor, and then that resistor light bulb is going back into the supply voltage. We also have a voltmeter connected in parallel to the bulb. So what in this experiment we're going to be doing is we're going to be moving the dial, and you should be able to see the voltmeter starting to go up. Okay, now we want this to get to 0.5, so that's a little bit too much. That's a little bit too little. Oh, it's quite sensitive. Okay, that'll do. 0.52. And at that point, we now see that the light is ever so slightly lit, and there is a current value. That's the current value we're going to write down for the first voltage. And then all we do is we just continue up. And we're going to go up to 1. Let's have a look. Oh, that's quite close, so we can get a wee bit closer. Oh, a wee bit too much. That'll do, 1.07. Doesn't need to be close. And then we see the bulb starting to light even more now. And we see that the current is now 0.12/3. Okay? And then we just keep going up until we get all the way up to 3.5. So if I get up to 3.5, there we go, roughly about there. I don't want to go too much because the light is now super bright. We can see that the final ammeter reading would be 0.22. And we would repeat the whole experiment again. So that's experiment for Ohm's law. Hope that makes sense. And if you're trying it at home or trying it in class, that's how we did the procedure. Alright, back to the teaching, National 5. Okay, and you're back. Okay, so you should have seen the nice setup and the experiment laid out and talked you through how it works. Once we have managed to get all the readings, we should look like something like this. Now, I've put some readings in from what my National 5 classes have got. And we've got an average, and we've got a voltage. And what we're actually going to do with this information, because there seems to be some sort of correspondence here, but we don't know exactly what it is. So one of the best things to do is look at graphs. Now, graphs can tell us a lot of information. And in this graph, we have voltage in the y-axis, and we have current, average current, in the x-axis. And what we're going to do is we're going to plot the lines. Now, to plot the lines, we'd be doing little crosses where all the coordinates are. So 0.5 and 0.035, and we'll be plotting it, and so on and so on. So we should have some dots that are probably directly going to be diagonal up the way. And if we were to do a line of best fit, it would probably look something like that. Now that's a very perfect graph, but it should look something like that. And we know that if there's zero voltage, there should be zero current. So we could say it could go straight through the origin, and it would go in an almost diagonal shape with that. Now, if you were doing this, your results would look different depending on your results, of course. Okay. Now, when we do that, and I'm going really quickly through this because it would be an experiment you would do in class, so I don't want to spoil that for you, but what you should find out is that current and voltage are directly proportional, i.e. when one goes up, the other goes up, but it goes straight from the origin. Okay? Directly proportional is only when your line of best fit goes through the origin. If it does not go through the origin, it is not directly proportional, but we know that this should be. Okay? So, from the graph, you're going to see the voltage and current are directly proportional. That's a relationship. That's us answering the A. This is because it is a straight line passing through or close to the origin. Alright? Now, let's take a straight line. Y equals mx. That's something you should know. And let's just put in the values that we had. So we had voltage for y-axis. We had current for the x-axis. Alright? So this is the amazing thing. If we can find the gradient, i.e. do y divided by x, or v divided by I, doing the equations of the gradient of an equation, or equation of a gradient, is m equals y2 minus y1 over x2 minus x1. And we should find out that if we do v over I, because that would be v2 minus v1, and I1 over I2 over I minus I1, okay? We actually find out that v divided by r gives us the current, gives us the resistance. So v divided by I, the gradient of the line gives us the resistance. And it actually matches the 15 ohms that we found earlier. So we calculated out, we made sure that that was right, and we now said v divided by r, v divided by I, all these letters, v divided by I is the resistance of the resistor. So then we can rearrange it and we can say v equals IR. So by our experiment, by our gradient, we have proven that v voltage is actually equal to the current times resistance, because we know that voltage divided by current gives us a resistance using the equation of the line, and then verifying that with the fact that it matched the 15 ohm resistor that we measured initially. So we've just proved Ohm's law, that V equals IR. Now this is a fundamental equation in electricity and one that you should know, and we'll be using it time and time again. Now, we're going to just finish off with one thing, and we're going to do a wee calculation of V equals IR. Alright, so for V equals IR, we're just going to do this. And this question is asking us to calculate the resistance. So I'm just going to do what we had before, V over I. The voltage is 6 divided by the current, which is 0.3, gives us 20 ohms, because that's the unit of resistance. Now, I'm not going to spend too much time on that, because time is pressing. That is the equation. And I'm going to leave you with that, okay? Because that there is the equation that we're going to be using for a lot of electricity. V equals IR, voltage, current, and resistance. Okay? Now, Ashfab, you're doing a really good job. And it's November, we're going to have to keep working hard, but you're doing an incredible and really good job. So well done, every single person who's tuning in. And remember, like and share. See you later, National 5.